All right, so in this video, we're going to talk a lot about some limits. And in Calc 1, we were a little bit hand-tied as to what we could do sometimes because we know that if you plug a number into a limit as you're investigating, approaching from either direction or both sides, many times you could come up with an indeterminate form. From there, we would, in Calc 1, manipulate it algebraically, hoping to then be able to reevaluate and get something tangible. Now, we're going to be able to expand our idea of functions that we can work with here because now we're going to also introduce what's called L'Hopital's rule. But before we get into that, we need to talk about what are true indeterminate forms versus determinate forms. So I've got this table up on the screen, and this is a really, really good one to pay close attention to. Right now, we're going to focus in on the indeterminate forms. And in Calc 1, we discussed the 0 over 0 case. And that's the one where, again, you would then manipulate the function and hope you could reevaluate and come up with something. Now we're going to take it a step further and also define as indeterminate forms infinity over infinity, infinity minus infinity, 0 times infinity, 0 raised to the 0, 1 to the infinity, and infinity raised to the 0. So these are all indeterminate forms. Determinate forms, meaning things that we can draw conclusions from directly, hence the equals on all of these, would be what you see here. So keep these two things in mind. If you run into an indeterminate form many times now, we're going to be able to move forward using L'Hopital's rule. So L'Hopital's rule is a very, very helpful rule in figuring out these limits when you hit a certain indeterminate form. So the rule says that if the limit as x approaches a of f of x over g of x is going to either 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x, that original limit, is equal to the limit as x approaches a of f prime of x over g prime of x. Now there's a couple big takeaways from here. The first one is that assuming it goes to either 0 over 0 or infinity over infinity, so assuming it goes to one of those two cases only, can we then use L'Hopital's rule. If that's the case, then the original limit is equal to the limit of the numerator's derivative over the denominator's derivative. Okay, that's not a quotient rule. That's an individual derivative of a numerator divided by an individual derivative of the denominator. Okay, we'll get to these other cases down here in a little bit, but one thing to kind of keep in mind as we move forward, L'Hopital's rule deals with a quotient. We've got a numerator and a denominator. And so if you look at these other cases here, chances are we're going to have to do some algebra in order to create a situation that gives us 0 over 0 or infinity over infinity, hence then allowing us to use L'Hopital's rule. So that's just kind of something to keep in the back of your mind as we move forward. But for now, we'll take a look at a couple examples where we'll directly hit the acceptable L'Hopital form of 0 over 0 or infinity over infinity. Okay, so we'll take a look at this first example, and anytime you evaluate a limit, the first thing you do is always plug in the number. So you can see if you plug a 0 in, you would get a 0 over 0, which is an indeterminate form. Now, because we've hit the 0 over 0, we can now move forward with L'Hopital's rule. So off to the side, I'm going to write LH for L'Hopital, and then I'm going to continue with the limit notation. Remember, for limits, the limit notation needs to be before each step unless the variable is gone. So limit on every single step. Additionally, I want you guys to get in the habit of writing LH anytime you run L'Hopital's rule. That's going to make grading your work much easier to understand. So now, for L'Hopital's rule, this is equivalent to the derivative of the numerator, which the derivative of our numerator would be 2 cosine 2x, divided by the derivative of the denominator, which would be the 5 cosine 5x. At which time now you're ready to go ahead and reevaluate. These cosines at 0 would go to 1, leaving us with a final answer now of just 2/5. So L'Hopital's rule makes this very, very easy compared to what you might have had to do in Calc 1. If you remember, this is a Calc 1 limit to where you could take full advantage of the fact that the limit as x approaches 0 of sine x over x equaled 1. So if you go back and review your Calc 1 notes, we would have had to break this apart and to take advantage of this property here. But now in Calc 2, we have L'Hopital's rule, which you can see takes us directly to our solution. Okay, so in this example, we've got our limit taking us to positive infinity of e to the 3x over x squared. Now you can't really plug in an infinity, but you can conceptually think of x being a really, really big number. If x is a really, really big positive number, then when I plug that in up here, you could see you would get the infinity on top as well as the infinity on bottom when you plugged in that really big number. So this is an indeterminate form and one of the two acceptable indeterminate forms that allows us to move forward with L'Hopital's rule. So I'm going to write an LH next to it, and I'm going to continue my limit notation, taking the derivative of the numerator separately. I'm going to get a 3 e to the 3x, and in the denominator separately, I get a 2x. Well, if you now take your really big positive number and evaluate the top and the bottom separately, you actually again end up with an infinity over infinity, which means we just need another iteration of L'Hopital's rule. So we'll essentially do the same thing now to this numerator and this numerator. From here, our derivative would be a 9 e to the 3x, and in the denominator we would just have a 2. Now, you can see when you reevaluate it at a positive infinity, you're going to get a positive infinity on top with a 2 on bottom, which means that this whole thing now trends off to positive infinity. So there would be our final answer for that one. So there's nothing that says you can't continue iterations of L'Hopital's rule, but it is important that you always have a 0 over 0 or an infinity over infinity before you apply this. Now, when we come back and we look at this problem from the start, keep in mind also that this result is a little bit obvious if you really think about order of growth. Now, there'll be an entire section on order of growth at the end of this chapter, but just the little bit of insight right now might help you with certain problems. We know that an exponential function is much greater than a polynomial function. So if we have a larger quantity over a smaller quantity at infinity, it makes sense that this thing's going to trend off to positive infinity. All right, so for this example now, we've got another limit as x goes to positive infinity, but you can see if you plug a really, really big number in for this guy and this guy, what we're going to end up with is an infinity minus infinity, which is in fact an indeterminate form, but unfortunately not one that we can use L'Hopital's rule for. So how do we put ourselves in a position to use L'Hopital's rule? Well, the only two acceptable indeterminate forms would be a 0 over 0 or an infinity over infinity, both of which have numerators and denominators. So it's going to make sense for us in this problem to manipulate this function so that we have both a numerator and a denominator. The easiest way to do this is just by multiplying top and bottom by the conjugate. So if I multiply top and bottom by root x plus 1 plus root x, then that's going to officially give me a numerator and denominator in hopes of coming up with an appropriate L'Hopital's form. If not, then we'll figure out where to go from there. So when I multiply this out, in the numerator I would have an x plus 1 minus an x, and in the denominator the root x plus 1 plus root x. So if I simplify this down just a little bit, in the numerator I have 1, and in the denominator nothing really changes. Now, if we take a look at this, this actually gives us, in our case, a 1 over infinity. Well, 1 over infinity, while it does have a numerator and a denominator, does not match up with either of the acceptable L'Hopital forms. That being said, let's take a closer look at what we have. if you look at that numerator, that's always a 1. But if you look at the denominator, you've got an infinity plus an infinity. Well, infinity plus infinity is not an unknown. Infinity plus infinity is still infinity. So what we're looking at in terms of a big and small ratio is something small over something big. Anytime you have something small over big, as you go to infinity, that ratio then limits at 0. That's the same idea that we discussed when we were talking about even horizontal asymptotes, for that matter. The small over big ratio at infinity would always give you that 0 quantity. So no L'Hopital rule needed here, even though the thought process initially was to construct that denominator to get one of our forms. We actually didn't need it, with just to use a little bit of logic.